So now we're going to work a couple problems involving work, energy, and power. So our first problem, we're going to lift a box against gravity. So gravity is mg. You're going to apply a force. We're going to call this the person. And you're working against gravity. So our distance is going to be up 5 meters, which is in the same direction as this. So this theta equals 0. You know that work equals force dot displacement vector, which equals force times distance cosine of theta. So cosine theta, this is 0 degrees, so this is 1. Your force is, again, the force of gravity. It's balancing force of gravity. So you get your force is equal to mgd times 1, which equals 30 kilograms, 9.8 meters per second squared, times 5 meters, which is, your work equals 1470 joules. Alright, now let's try another example where they're not exactly aligned. So we've got a person pulling a wagon now. So here's your wagon. They're pulling it with some force, 575 newtons at an angle of 25 degrees. So your delta x in this case is 3 meters. So the problem asks a couple things. First, let's find the work done. So work equals FD cosine theta. Again, it's the angle right here. So since this is our direction, we want this part right here, which would be your F cosine theta. So if we're looking at this, we get equals 575 newtons times your distance, 3 meters, times cosine 25 degrees. And we get the total work done equals 1560 joules. That's the work done. Now we're interested in power. So if we're looking at this, we know that, here, I'll do this one in yellow, power equals work over time. So this would be 1560 joules over 20 seconds. And you get that your power is equal to 78.2 watts. Power is just how much work you can do in a given amount of time. Let's go work a conservation of energy problem. Okay, so in this problem, we have a pinball sitting right down here. We're going to pull back a spring, and then we're going to let go of the spring. It's going to hit the pinball, send it up into the air on the table. And we're going to find two positions. How far was the spring pulled back? And then we're going to find out how fast is the ball going. So this is a conservation of energy problem. Right now you've got all potential. It goes to kinetic right here, and then eventually it goes to all gravitational potential. So if we look at this, whenever you start any force problem, you get work done by external equals final energy minus initial energy. Alright, we know that there is no external work, so you get E initial equals E final. Let's work this first part real quick. So we know that it goes up at the beginning. All we have are spring energy, kx squared, equals, at the end all we have is potential energy. And what we get from this, we get x equals square root of 2 mgy over k. And please work through this and try to figure out how we make these conversions. Make sure I'm not doing any math mistakes. And eventually, you will get that your spring is pulled back a distance of 0.02 meters. And that's how far you pulled that spring back 2 centimeters. So if we look at the next part, so we're looking at how fast the ball is going. Well, what do you know about from here, where the ball's at the top, compared to all your energy is in the spring, to right here where it's just going, all right? So right when it leaves here, and I guess it's going this way, zoom, well, straight up. All right. So you know that the energy is conserved. All that means is that your energy's got to go somewhere, and since you have your external work equals energy final minus energy initial, there is no external work. You can pick the final and end point anywhere. So I'm going to pick right here because I know it there, and it's all kinetic. So if it starts, again, this is just going to give you E final equals E initial. At the top, your final, well actually, sorry, that's your initial. You have mgy, all potential from gravity. At the bottom, you have 1/2 mv squared. You'll notice these masses cancel, and you get V equals square root of 2 gy. So this is, I'm going to bring this up here, square root of 9.8 times 0.4. Your velocity, right when you leave that launch pad, is going to be the square root of 2 times 9.8 times 0.4, which is 2.8 meters per second. All right, let's work another one real quick. So this one is a little bit different. We've got a cliff, and this cliff is green. And this person's going to jump into, I will make this distance, 4 meters, jumps into some muck. This muck is blue, looks like water, and goes down in 1 meter. So here's your person. And this muck is going to stop him. I'm going to give this person a little adventurer hat. Alright, so they're going to jump in the water, and it's going to stop them. So here, you're stopping, this is not a conservative force. This is work external equals energy final minus energy initial. So let's look at the parts. Work external, this is going to be some force times distance cosine theta, because that's what work is. And in this case, that work is going to be provided by this little median. So I'll draw a stick person, they're going to end up in here. Alright, so that's where that person goes. Now, that's muck right here is going to provide the external force. If we look at the energy final, this is 0. All of that potential energy and all that kinetic energy is going to end up being lost in the muck, minus, they have potential energy at the beginning, mgy. So let's make y equals 0 right here. This ensures that they have no potential energy at the end. We know that the stopping force is going to go this way. So this F vector points this way. However, delta x points this way. So here you have theta equals 180 degrees, which means that this cosine right here is minus 1. So what do you get? You get negative FD equals negative mgy divided by negative 1. And you're going to get force equals mgy over distance, which is 3,675 newtons. That is the amount of force that that muck applies to get you to stop and take all your energy from potential to kinetic just before you hit the muck. And in this case, sorry, this distance, we need to talk about this. This y, 5 meters, because you start 5 meters above. This distance is the distance the force acts on you. So this distance is 1 meter. Okay? I hope that helps, and I hope that makes sense. So again, 5 meters, because that's from y equals 0 to where you end up, 5 meters. And distance, how long or how far that force acts on you, it's only acting on you for this meter right here. And we've got one more example to talk about power. Alright, so our final equation, we're going to talk about how power is equal to Fv, F dot V, right? Which equals Fv cosine theta. So we're going to tilt our axes. Okay, we're going to draw them this way. This is going to be y hat. This is going to be x hat. V is in the direction of x hat. So if we look at this, you are going to have to overcome this part right here. Alright? So to overcome this, you have to exert a force in the x direction. So sum of forces in the x direction equals max. You are not accelerating. So whatever we'll call this, here, let's actually draw this in here. This is force person. So you're going at a constant speed. So you know that the force of the person minus mg, in this case this is sine theta, equals 0. So the force this person is exerting is mg sine theta. And if we pay attention, since the force of the person is going this way, it's in the direction of x, so when I used this sine theta right here, I actually aligned these two forces in a row. So you'll get your power is equal to mg sine theta, and if you wanted to look at this as cosine, now that they're in line, that's cosine 0 degrees, times velocity, and you get, we know mg sine theta, this is 75 kilograms times 9.8 meters per second times sine 65 degrees times 1 times 3.8, and you get a grand result that your power is equal to 2530 watts. So key things to watch out for: look for which way your force is going and which way your velocity is going. I hope that helps, and good luck.